Okay, so maybe we can start. So I am very happy to welcome Professor Ryan O'Donnell, who spent the last few days here in the IMS conference workshop. So Ryan is Canadian. He lives in the United States. He is a professor at Carnegie Mellon University. He studied BA or BA in Toronto. Then he got a PhD from MIT. He was postdoc in IAS and then, I guess, Microsoft. And since then, he is working in Carnegie Mellon. So Ryan's interests are extremely wide. He did significant contributions in, complexity theory, learning, testing, approximation algorithms, and in particular, anything which is related to Boolean functions. And I won't speak that much about his result. He will speak himself. But I would like to say that the book he wrote about Boolean function is kind of dream book. You ever write a book, try to copy that one. So it's amazing. You can download it freely on the web. I really don't know why don't you charge something.
You can also buy it if you want.
You can buy it. So
Yeah.
You can also buy it. And so to be short, because he has very soon to catch a plane to go to the scientific capital of the Barbados. So let's welcome him with his talk about learning and testing.
All right, thanks, Miklos. Yeah, it's great to be here. I always wanted to visit Singapore, so I'm very happy to have come. Let's see, yeah, I guess there's a mismatch between the title on the slides with the title on the poster, but it's the same talk. It's a bunch of stuff mixed together. And this is joint work with John Wright, who's sitting back there. He's got a blue shirt. So if you have any questions, you can just ask him. Okay, right, so this is a talk about quantum stuff. So let's suppose you're like a scientist, like a quantum scientist at the Quantum Center for Technologies, and you have a quantum machine like this, some kind of crazy device, and it has like a red button on the side right here. And then every time you hit that button, the quantum machine like does its thing. It's like an apparatus, and it spits out like a quantum state. That's, I guess, my picture of like what half of the people here do day to day, I assume. Great, so as you probably know, like a state of a quantum particle is just like a unit vector in some d dimensions. And d is the dimensionality of the particle. If it's a qubit, then d is 2. If d is bigger than 2, then it's called a qdit. But anyway, so that's the state of the particle, some unit vector. And of course, like, if you ran this machine and it popped out this particle, you probably want to know what state it is. But probably also, as you know, I guess all of you know, you could try to like measure this particle and find out what state it's in. But that doesn't like really work so well. When you try to measure the particle, you don't find out what state it's in. You only get some probabilistic information about what the vector was. And then the vector is like destroyed, so you can't repeat this process. And what does a measurement mean? I guess maybe also a lot of you know this, but for example, the main thing essentially you can do is this thing called projective measurements. This won't be very important for the talk, but roughly speaking, what that means is you get to rotate space according to your favorite unitary matrix U, a d by d matrix U. And then when you do the measurement, you see an outcome I, 1, 2, 3, 4, up to d, with probability proportional to the square of the projection of the rotated vector onto the ith coordinate axis. Okay, this is essentially almost the most general thing you can do. And we may mention that later. Okay, so there you are with your machine. And it's actually worse than this because I slightly lied to you when I said the output of the machine, a particle, its state is like one vector. Actually, the machine itself could be probabilistic, right? Like maybe this crazy contraption, the first thing it does is flips a coin and does a different thing depending on whether it lands heads or tails. Or maybe the machine itself does some like internal measurements of some particles involved in the system, which as we just saw are probabilistic. So really what actually you get out of any quantum apparatus is a probability distribution over unit vectors. So this is what we'll kind of be studying in this talk. You have some probabilities, P1 through PD, of this machine outputting these different unit vectors, V1 through Vd. And due to the laws of quantum mechanics, you can assume that these vectors are d orthonormal vectors in C to the d. Okay, if you know this terminology, I mean, really it outputs a mixed state. That's all I'm talking about here. And the p's are the eigenvalues, and the v's are the eigenvectors. But I prefer just to think of it as like a probability distribution over like some unit vectors in space. Okay, great. So your life is looking a little tough because you have like an unknown probability distribution, P1 through PD, over an unknown set of d orthonormal vectors, V1 through Vd. And then you can't even just like look and see what the outcome was. Like measuring only gives you some probabilistic information about what the outcome vector was. So that's like a triple whammy. You're really in unlucky shape here if you're trying to understand the output of your machine. So what can you do? Well, the thing that you can do is you can hit that button that generates the particle more than one time. Okay? I mean, you're not going to be able to get a lot of information at all if you can only measure once. So imagine you can run that quantum experiment, n times. Every time you run it, it costs you $10,000 or $100,000. So you want to not run it too many times. And you want to find out, maybe by doing bigger measurements or more measurements, what is the state that this machine outputs. Okay, we assume that every time you do it, it gives you an independent draw from this probability distribution on unit vectors. Or if you know this formulation, you get like rho tensor to n times. Okay, so for an example, let's say it's a three-dimensional particle and you hit the button 7 times. So then one thing that might be the actual outcome is, V1 and then V3 and then V2, et cetera. There's 7 things here. And that occurs with the product of the associated probabilities. They're independent draws when you do this. So you get this succession of 7 particles with this probability. And actually, the mathematical way you formulate this is not with like a list, but the proper way to represent these 7 particles is by a tensor vector. So overall, like every quantum state should really be a unit vector in some complex space. So really, the outcome in this case is this tensor of these 7 vectors, and it lies in C3, like 7 tensor copies of it. Okay, it's not like super important to get the mathematical formulation of this if you haven't seen it before. Okay, so that's what happens after you hit the button n times and get like 7 copies of the particle. And now you can have like 7 particles. You can like measure the first one, measure the second one, up to measure the 7th one. And each one could be like this thing where you rotate space some way and then get I with probability proportional to the square of the projection on the ith axis. And then you gather some information, hopefully try to figure out overall the distribution of the p's and what the v's are. But actually, you can even do something better than that. You can just think of this as like one big unit vector in a big space, and you can do like one gigantic measurement on the space. And that's sort of even better, and this like encompasses the possibility of measuring them individually, and it's an even better thing for you to do. So you can do like, if you want, like one giant measurement where you rotate this d to the n-dimensional space and project onto one of its axes. Okay. Any questions so far, by the way? Okay. Maybe, I don't exactly know the audience. Maybe everybody knows this stuff. But anyway, I'll go on at this level. So what are some problems you might have here? I mean, one is this one that we just said. I mean, you want to just learn the state that this machine is outputting. In particular, you want to learn these probabilities P1 through PD. And you want to learn these vectors V1 through VD. Okay. Now, of course, in any kind of learning problem like this, you're never going to learn them exactly. So there's some error tolerance epsilon that you hope to learn them up to. And also, you're never going to be able to do this with 100% probability. Everything's probabilistic, so you hope to do this with high probability. But I'm going to totally ignore this with high probability in the talk and also downplay this epsilon parameter and just say you're trying to learn these things approximately. Again, if you're an expert here, I want to actually learn the density matrix rho up to some epsilon in, let's say, trace distance. But just think of it at a high level like this. So that's the most natural problem. Just learn everything about this state. Okay, now that may be very expensive. I mean, we might eventually show that in order to do that, you're going to have to hit the button a lot of times. So maybe you want to conserve on how many times you hit the button and be willing to learn a little bit less about the state. Oh, this is called quantum tomography, by the way, for some reason. Does anybody here actually do quantum tomography? I heard like people actually do it. I wonder if you're like sitting in the back there somewhere. Well, anyway, I would have some questions if you do, because I don't know anything about the practice of this. Okay, so as I was saying, you maybe want to learn less if you can do that with like fewer samples. So another thing you might want to do is just learn the set of probabilities, P1 through PD. And I should mention, by the way, there's no like inherent ordering on 1 through D, so it doesn't make sense to really learn the list P1 through PD. You should just learn the set P1 through PD. Again, if you know the notation, the terminology, this is like learning the eigenvalues, the spectrum. Okay, and again, this is up to some epsilon accuracy and total variation distance or something. And this is called quantum spectrum estimation. Okay, and that's also like maybe a natural thing to do. Like you might want to know what is the entropy of the state, and the entropy of a quantum state doesn't actually depend on the vectors, it only depends on these probabilities. It's just the normal entry of this as a probability distribution. Okay. In fact, you might not even want to go this far. You might only want to know if these probabilities satisfy some certain property. You don't care to learn them exactly, you just kind of want to know something about them. For example, like one thing you might want to know is it true that this P1 through PD is the uniform distribution? Like they're all equal to 1 over D. And that has like some physical significance. That's called the state being the maximally mixed state. And like maybe you hypothesize that your machine outputs a particle in the maximally mixed state, and you want to kind of test that hypothesis. Okay? Or you might want to check maybe at most some R of these are non-zero. That's called the state having rank R. It's kind of like the state sort of secretly actually lives in a low-dimensional R-dimensional subspace, even though the ambient dimension is D. And this is also, I think, considered something that might happen in practice. Like maybe you think that the machine outputs a pure state, that means a rank 1 state, and you want to test this property. Okay, and let's quantum spectrum property testing. And maybe the last thing I'll mention is maybe you want to do this thing, but maybe you also feel that probably actually there's only a few vectors and probabilities that are relevant, like maybe a few probabilities that are large. Maybe you feel that like there's only like 3 large values of P, and so you want to learn what those 3 large values are and the associated V's, and you don't care about the rest. So you might want to learn just the top PIs and the associated VIs. And that thing is called quantum principal component analysis, or quantum PCA. Okay, so it's a generalization of number 1 when K is D. Okay, and there's even other tasks you can invent, but I mean, like these are examples of things you might want to learn about or test about your unknown state. Okay, so in a couple of papers recently with John, we have some new results about how many samples you need to do this and how many samples are required to do this, how many suffice and how many are required. And I'll mention some of the results, but I want to actually focus more on the methodology than the results in this talk. But anyway, one thing we show is that for this one, you can do it with order d squared samples. Okay, there's an epsilon parameter too. It's like d squared over epsilon squared, but it's like d squared samples. And the previous best result had d cubed here. And actually, I should mention that in independent work by Ha et al., they got a similar result with basically the same thing. And let's see. For this one, I changed it a little. Just if you want to learn the k largest PIs, we showed that you can do this with k squared samples. And that's kind of nice, actually, because it doesn't depend on the dimension at all. So that's like one of the few kind of results in this area that has no dependence on the dimension. If you want to learn the top k PIs and also the associated VIs, we show you can do that with k times d samples. And that actually is a strict generalization of this one by taking k to be d. I don't think there are any previous results about that, other than just learn everything. This one, testing if it's the maximally mixed state. I mean, one thing you could do is use this to learn all the V's and the P's. That'll particularly tell you the P's, and then you could sort of just check if they're all 1 over D. But actually, you can do something better than that. We showed that D samples are necessary and sufficient for this. And yeah, I guess I can also mention that d squared samples are necessary for this problem too, so it's a tight result. Okay, so we have like various results about this, and I'll tell you something today about how we try to obtain them. And for simplicity in today's talk, I'm only going to talk about problems that involve learning or testing properties of the probability distributions, the P's. That already makes the problem interesting enough. And in fact, as it turns out, like our algorithms that also do things like learn the V's, they're based on some of the same technology we use for problems just involving the P's. So for the remainder of the talk, we're only going to be worried about learning or testing properties of these probabilities. Okay. So as I said, I'm not going to exactly tell you much more about the results, but I want to tell you what I think is quite interesting is the methodology about how you go about proving these results and analyzing this tomography type problems. Okay, so to warm up for this question, let's go back to this problem that we're facing. We have this unknown probability distribution P1 through PD on unknown vectors V1 through VD. And we're trying to learn all these. Maybe we're just trying to learn the P's. So let me consider a special case that will kind of warm us up for the main problem. let's imagine that these v's are actually not unknown. Let's imagine that they're actually known to you. You just, for some reason, you know that the output of this machine, you know the vectors that it could output. You just don't know with what probability it outputs each vector. Now, in that case, that's a very happy case for you because you don't need to worry about how you should measure the vectors. It's obvious the best thing you should do is just measure each of the particles individually and just always do the rotation that puts v1 through vd at the standard basis. And then when you measure, you'll just exactly learn what the outcome was. Okay, so every time you hit the button, you can do a measurement that's not probabilistic. You'll just learn which of the known v1 through vds it was. So in that case, it actually becomes totally equivalent to like a purely classical problem. Learning or testing an unknown probability distribution on D objects. It's like a problem that's like maybe one of the most basic problems in all of statistics. You have the ability to get samples from a probability distribution on D things, and you want to like learn the probability distribution or test some property of the probability distribution. You know how many samples you need to take before you can, with high confidence, learn what you want about the probability distribution. Okay, so that's a purely classical problem that's been studied a lot. And you can actually ask all the same questions that we mentioned for the quantum problem about just this classical problem as well. And they've also been all studied in classical statistics and computer science literature. So you might just want to learn all the p's, again, approximately with high probability. Or you might just want to learn the set of p's. Or you might just want to determine, like maybe you hypothesize that you're getting draws from the uniform distribution and you want to sort of check if that's the case. Maybe if you're like testing whether like the lottery is actually using a uniformly random number generator for its draws. Or you might just want to like learn the largest k PIs, again, etc. You can invent lots and lots of different problems in this area, and people have invented lots and lots of different problems in the area and analyze the same question, like how many samples do you need to do these problems effectively. And actually, although it's a very basic setup, it's a little bit surprising that like even some of these questions were only resolved within the last 10 years, even they seem like very basic questions. For example, this one, trying to tell if the distribution you're getting samples from is the uniform distribution, it was only in 2008 where they showed that square root d many samples are necessary and sufficient for testing this. Okay, so like all of these problems that exist in the classical distribution testing worlds have quantum analogs. So this quantum problem of tomography and PCA is kind of a generalization of all this classical stuff.
So for 3, I mean, the promise is a constant gap, or?
Yeah, this would be, I mean, if you know what this means, this would be like in the property testing model. So probably you want to distinguish between its exactly the uniform distribution versus its epsilon far from the uniform distribution and total variation distance.
Yeah, and epsilon is a constant.
Yeah, I mean, you can even care about non-constant epsilon. So like the actual best query complexity for this is root d over epsilon squared, I think. Yeah. Any other questions? Okay, so let me also, since we're going to try to build up the methodology for the quantum problem, let's try to build up the methodology that we would even use for these classical problems when we only care about properties that depend on the set of probabilities, P1 through BD. Okay, so let's figure out the methodology there. And what does this mean, by the way? I'll explain more in the other slides, but properties that only depend on the set, these are properties of the probability distribution that don't really care about the names of the elements 1 through d. They sort of only care about the values. So things like, is it the uniform distribution? Or are at most r of them non-zero? Like you don't care which ones are non-zero. You just only care that at most r of them are non-zero. Okay, so let's imagine like we were trying to solve one of these problems. Like we got draws from a probability distribution. We're trying to test if we feel it's like the uniform distribution or close to the uniform distribution or some other property like that. So what might we do? Okay, so like let's say d is 5 and we do 20 samples, so far, and we'll get like an outcome that looks like this, 20 numbers between 1 and 5. So I want to think about what we're going to do with this data. And there's a few simplifications we can make. So we actually get this as the data coming into us, but like since we only care about properties like this, we can sort of without loss of generality, throw away some of the information we got. So the first idea to notice is that permuting the n positions here doesn't really matter to us. Really, we don't care that we got these numbers in this order. We just care that like we got 5 like 4 times, and we got 1 like 3 times or whatever. Okay? And that's because we assume the draws here are independent from the distribution. In other words, like we don't have to remember this string. We can just remember the histogram of values that we saw. Okay, so we can just, here's the histogram. We saw 1 4 times. We saw 2 3 times, etc. Okay, and it's without loss of generality always to just remember this. So that's a nice simplification we can make. The next simplification is only a little bit more complicated. It's the following. So I'm imagining again that I only care about properties that don't really depend on the identities of the names like 1 through d. They just care about the values p1 through pd. In other words, another way to say that is like you permuting the d symbols, like renaming the elements, like doesn't matter to you. So it's, for example, you don't really care that you got element number 1 4 times. You just care that you got something 4 times and something 3 times and something 3 times and something 6 times, etc. Okay? And because of that, you also, it wouldn't really matter to you if you permuted these rows as well. So for example, a simple thing you could do is just sort this histogram by putting like the largest row at the top and so forth on down. In other words, like moving it to this. And what I'm saying, this picture is sort of representing that for the original string, the only thing that you really care to remember is that some element, the most frequent element in your sort of input, appeared 6 times. The second most frequent element appeared 4 times, etc., down to the last element appearing 3 times. Okay, and for example, presumably if you wanted to test, is this distribution, I'm getting draws from the uniform distribution, you'd probably like look at this and see if like about all the rows were the same length. Or if you wanted to see if the support size is at most r, you would sort of check that like there are at most r non-zero rows. Something like that. Okay, so this picture, as I said, this represents the number of times you saw the most frequent element and so forth. And I'll give these names. I'm going to call lambda 1 the number of occurrences of the most frequent element, lambda 2, lambda 3, down to lambda 5. And in fact, if you've studied some combinatorics before, this like kind of object has a name, like a sorted histogram. In combinatorics, they also call it a Young diagram. It's just a sorted histogram, something that looks like this. And you usually write like lambda for it. So that's why I called the rows lambda 1 through lambda 5. Okay, so just to summarize, the story we've told ourselves so far for the problem of learning properties of an unknown distribution where you don't really care about the names of the elements, it's just a property depending on the values. There's 2 symmetries that were involved in this problem. The symmetry, this is the symmetric group on n positions. The invariance of permuting the n positions or the n outcomes, we didn't care about that. And there's also invariance of permuting the names of the d outcomes. That's the SD symmetry. And you could sort of factor these out and say without loss of generality, instead of imagining that the learner gets the whole string of draws, we may as well just tell the learner a random Young diagram lambda, which is the sorted histogram of the draws that it obtained. Okay? And this lambda will always have n boxes and d rows. And this is like a small remark, but given P1 through PD, you could write down a pretty simple expression for the probability of seeing any particular lambda, any particular sorted histogram. It's, this is like combinatorics 101. It's like some symmetric polynomial expression in P1 through PD. It's just a small comment. Okay, and then the game would be you get like lambdas, these sorted histograms or Young diagrams, from this probability distribution, and you're trying to infer something about the p-values. Okay, that's the end of the classic story. Now let's remember the real problem we're trying to solve is the quantum version of this problem, where you actually have probability distribution over vectors, and these vectors are like unknown to you. Well, it turns out this also has a very similar pair of symmetries. We still have this invariance to permuting the n outcomes. I mean, since we get independent draws from this machine. But now we have a kind of a different invariance for the objects that are the outcomes themselves. We don't imagine that we just can permute them, but what we really have, the objects are like an unknown set of d orthonormal vectors, and like everything should sort of be the same if you applied any rotation to them, or I guess this is a unitary matrix here. So we kind of have these two symmetries in the problem, which we'd also like to sort of factor out without loss of generality. And long story short, I'll skip this, but you can factor these out in like a principled way. It uses something from group representation theory called Schur-Weyl duality. And in fact, if you know something about representation theory, which I didn't before I started these projects, you may know that like the representation theory of these two groups also happens to involve Young diagrams, which is a little bit funny. And here's the upshot. When you're quantumly learning a state and you only care about the properties or learning the probabilities, it's again like without loss of generality that you'll say like, never mind giving me all the particles, I can just get a Young diagram without loss of generality. In other words, it's like saying that there's some measurement, big measurement that you can perform without loss of generality, and the outcomes of that measurement are Young diagrams. But it's not the same distribution on Young diagrams as in the classical case. You don't just get like the sorted histogram of the outcomes. You get some like weirder distribution on Young diagrams that depends on the probabilities. Okay, and I'll tell you about that now. So it's going to look less weird than this later, but if you just write down everything with the representation theory, then the probability distribution on these Young diagrams you get out in the quantum problem also can be expressed as some symmetric polynomials of the p's, where like this symmetric polynomial is something called the Schur polynomial, which combinatorialists love for some reason, even though it's complicated. And this constant factor is like the number of standard Young tableaus with this shape. It's some like explicit polynomial. It's not the nice one from the classical case. So this looks good in the sense that like, okay, we've kind of eliminated all the vectors and the quantum and stuff from this whole problem, and we've just reduced to like understanding if you get a random lambda with this probability distribution, what can you infer about the p's? That's the good news. The bad news is this is some like weird, complicated thing. But there's some good news, which is that actually there's a nice way to describe this probability distribution, or a somewhat nice way to describe it. It has a combinatorial interpretation. And it's this. I'll tell you a random process which generates these Young tableaus, these sort of sorted histograms, with exactly this probability that comes out of the Schur-Weyl blah, blah, blah. It goes like this. First, pick a random string, like a random word W, with n symbols, where each symbol is drawn independently from the pi distribution. Now, if it was just the classical case, then like that would be it. Like then the learner would get W and it would try to do its thing. Or we could say without loss of generality, the learner would get the sorted histogram of W. But it's a little bit worse than that. You take this word and then you apply to it this algorithm called RSK algorithm, which I'll say more about later. But this is like some combinatorial algorithm originally invented in like the 30s. This K is Knuth, who's like a computer scientist. So like has nothing to do with quantum or anything. You apply this RSK algorithm to W. And it turns out that this RSK algorithm outputs one of these Young tableaus. Okay? So I'll say more about the RSK algorithm in a second. But basically, now the game is like this. There's some unknown probability distribution, these PIs. And like somebody like picks you get to specify n. And then somebody picks a random word where the symbols are drawn from this distribution. And then you don't get to see that string. It gets passed through this interesting combinatorial algorithm. And you see the output of the algorithm. And then you have to try to infer something about the PIs. OK, so what is this algorithm? RSK stands for the inventors. It's like Robinson, who is a sort of distinguished Canadian mathematician, and Schoenstedt, who did several things, and Knuth is the famous computer scientist, Knuth. And I won't tell it to you because like telling you exactly what it does would take like 9 minutes or something, and I don't want to do it in like 30 seconds. I'm just going to draw like a picture of like it operating on this string, and you can see like it does some algorithm that builds like a succession of boxes. basically, like, it operates symbol by symbol, and when it's on, like, let's say 3, it tries to put this 3 into the diagram in the first row, but there's this property that, like, the numbers in the first row have to be increasing, so, like, when it comes in, like, here the 5, it had to bump out, and it, like, inserts it into the second row. Basically, you try to put the number as far to the right as you can while maintaining that this is increasing, and then if you get stuck, you, like, stick into the first row in the last place it can go, take the number that was in there, and, like, recursively do it in the second row. So, I mean, obviously that was, like, way too fast to understand exactly what's happened, but it's like something like that. I mean, you can write down the algorithm in, like, 2 lines. And it processes the characters one by one and, like, adds a box to this diagram every time it processes a character. And then you should imagine that the very last step is it erases the numbers, and, like, that's the output. So, like, you know, it's done properly. Like, if you plug this particular string into the RSK algorithm, it outputs this particular Young diagram. Yeah, sure. Here you go. Ready? Go. Let's see if you can figure out how it works. All right. Like, here comes the 1, and then the 3 went to there, and it bumped it down. Yeah. So you can imagine, like, it's not super simple. So, like, the problem of, like, I give you the output of this algorithm, and you have to infer something about the probability distribution that generated this string, that's a little complicated. But it's not super crazy either. Maybe you can imagine it. And in fact, I mean, the one reason why I don't, like, go into more details about this algorithm is I'll tell you, like, other way to look at this algorithm, which will be even more fruitful for us. Okay, so RSK is, like, some algorithm that was, like, studied by combinatorialists for their own purposes, as we'll see in a second, that maps a string into, like, one of these Young diagrams. So it maps this particular string to this one. And here's, like, other way of looking at it. And this is actually concerned with the reason that they invented this RSK algorithm. The reason that the RSK algorithm was actually invented was to study like, the longest increasing subsequences in strings. So for example, I'll tell you something about the RSK algorithm. On any input w, lambda 1, the number of boxes in the first row of the output, is exactly equal to the length of the longest increasing subsequence in the word w. And increasing means, like, weakly increasing. So, like, you can have the same number, but just not decreasing. So this means that, like, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. If you think hard, there is some increasing sequence in here of length 9. And that's the longest one. Okay? And RSK was actually invented to kind of analyze longest increasing subsequences. In fact, if you know a little computer science, you could probably figure out, like, just what is the simplest algorithm for finding the longest increasing subsequence in a given string, some kind of simple dynamic programming algorithm. And that dynamic programming algorithm is exactly what sort of is going on in this crazy algorithm in the first row. So, oops, yeah. So the RSK algorithm in particular, it tells you the longest increasing subsequence in the string. But it's actually designed to give you even more information about longest increasing subsequences. Okay? So that's that. But there's a meaning to the length of all the other rows too, which is a little complicated. The first row is great. What is the deal with the number of boxes in the second row, lambda 2? Lambda 2 is such that you wish it would just be something like the length of the second longest increasing subsequence, but it's not quite that. It's like lambda 2 is such that lambda 1 plus lambda 2 is the longest union of 2 disjoint increasing subsequences you can get. Okay, so like lambda 1, the first row tells you about the longest increasing subsequence. The total number in the first 2 rows is like the length of the longest 2 disjoint increasing subsequences you can make. And then you look at the longest 3 disjoint increasing subsequences you can make, and that's the total number of boxes in the first 3 rows, etc. And for example, so by this characterization, right, the number of boxes in all the rows should represent the longest union of d different increasing subsequences you can have, where d is the number of different symbols. It's 5 here. And that's always n, everything. Right? Because why can you always partition any word into like d, or in this case 5, increasing subsequences? It's easy. You can just take all the 1s. That's an increasing subsequence, like weakly increasing. All the 2s, all the 3s, up to all the 5s, or all the d's. And that's d disjoint increasing subsequences, and that's everything. So if you can do d increasing subsequences, you can always get all n characters. And sort of these rows tell you statistics about like how much you can get if you give yourself 1, 2, 3, etc. increasing subsequences. Okay, so I don't know if you can make sense of this, but like I tried to illustrate here. Like this is the length 9. The yellow guys are the length 9 increasing subsequence in this word. And then the yellow and the red here, which is like unreadable, are like 2 subsequences that collectively have 14 characters in them, and so forth. And in the last line, I just highlighted, you know, like all the 1s, all the 2s, all the 3s, all the 4s, all the 5s. And this is like a little bit more tractable to analyze, you know, combinatorially or probabilistically. So, I mean, what we saw is that for the original quantum problem of trying to learn the spectrum of an unknown state, sort of without loss of generality, it boiled down to inferring stuff about the probabilities when you give a random word to the RSK algorithm. And that in turn is, you know, inferring something about the probabilities that generated this word by looking at this sort of longest increasing subsequence information. So it's still going to be hard, but at least it's like a, I don't know, combinatorial problem that you can hopefully understand. Okay. Yeah, like there's more information like encoded in this thing too. Like the height, the number of non-zero rows is always the length of the longest strictly decreasing subsequence, and there's other information buried in there too. Okay, so summary. P1 through PD are unknown probabilities. You, the learner, want to learn something about them or test them. You get to specify n. Then, like, you can imagine somebody secretly chooses a random word of n letters with the letters coming from this probability distribution. In the classical case, you would just get to see the sorted histogram of the draws. I'll call that mu. That's a Young diagram. In the quantum case, you get this like less informative thing, this more annoying thing, this longest increasing subsequence information, lambda. And you're trying to infer things about the probabilities from this draw. So, okay, how are we going to do this? Let's just try to get a little bit oriented to what's going on. So this is the situation. I want to tell you a little bit about something called majorization. So let's say this is the secret word, W, that gets drawn. And then this is the sorted histogram, mu, for this word. This is what you get in the classical case. This is what you get from running the RSK algorithm in the quantum case. Or this is the longest increasing subsequence information. And if you look at these two things, you know, one thing you would say by eyeballing it is that somehow lambda is like more top-heavy than mu. It's like more stuff towards the top. And that's always true. Lambda always majorizes mu. That's a simple fact, which means that the partial sums of lambda are always bigger than the partial sums of mu. And that's sort of for the same reason I just said. So for example, why is the first 2 rows of lambda always have at least as many boxes as the first 2 rows of mu? Well, the first 2 rows of mu tell you the number of occurrences of the most frequent letter or symbol plus the number of occurrences of the second most frequent symbol. And like you could always take those 2 symbols and just make the longest, make the increasing subsequence that just consists of all the copies of that symbol and all the copies of the other symbol. So like you can always get 2 disjoint increasing subsequences by taking the most common symbol and the second most common symbol. But you might be able to do something better. So that's why lambda 1 plus lambda 2 is always bigger than mu 1 plus mu 2, and similarly for any number of rows. So that exactly says that like this lambda will always be more top-heavy than this mu, the sort of histogram that you kind of wish you had. Okay, so that's the setup. So now let's see how we can apply it to some problems. So maybe the simplest problem you might try to solve in this case is estimate the largest probability. Okay, estimate P max, the largest probability. Okay, so let's first think about the classical case. You get draws from this distribution. You're trying to estimate the probability of the most frequent element. Well, you get the exact sorted histogram mu, and like the most frequent element is, it occurs a number of times that's equal to mu 1. You would just guess like mu 1 over n, right? That's like the empirical guess for like the most frequent element. And how good a guess is this? It's a pretty good one. I mean, this is a very, very, very easy analysis that everybody can do instantly. This will be an epsilon accurate estimate of P max with high probability if n is like order of 1 over epsilon squared. Okay, that's like Chernoff bound or something. Okay, so that says if you want to estimate P max classically, you can do it with this many samples, and that's necessary too. Okay, now what about the quantum case? We don't have mu, we have lambda. So it's not clear how to estimate P max. If you're just like, well, I don't know anything, like maybe I'll just output lambda 1 over n, like perhaps that's a good idea. I mean, at first you're like, it's kind of definitely not a good idea because lambda 1 is always bigger than mu1, so it feels kind of like this is always like an overestimate. But actually it turns out it's a good move. So what you're asking here is it true that the longest increasing subsequence, like lambda 1 is the very easy one to understand, right? It's just the length of the longest increasing subsequence. So is it true that the length of the longest increasing subsequence in a random word actually concentrates around p max times n? It's kind of like saying, basically, is it true that the longest increasing subsequence is basically as long as just like taking all the most common elements? That would be p max times n. Or is it possible that you can sort of always do better than that? And it turns out actually it does concentrate around this number. You know, if I gave you like 10 minutes to go home, you would probably be able to prove something like this. This is not too hard to show, that this will be actually an epsilon accurate sample if n is something like maybe up to logs like d over epsilon squared. But what John and I proved, one thing we proved, it's a bit harder, is that same thing, maybe with a worse constant. N just has to be like constant over epsilon squared, and you'll get an epsilon accurate approximation of lambda 1 out of this. And what's a bit funny is our proof, it's pretty non-elementary. Like it uses the representation theory and everything, which looks weird. Like it looks like if you take anything out of this talk, like I encourage you to like take this home as a problem to just like think about yourself. Like try to show that if you do a random word of length n from an arbitrary distribution, and you look at the length of the longest increasing subsequence, it'll be p max plus or minus epsilon times n, provided n is like 1 over epsilon squared. I mean, that's like a purely simple seeming combinatorial problem. We could only solve it with some kind of non-elementary tools. And this O is like a totally universal constant. It's like 8 or something. It should be 4, but we got 8. Particularly, it doesn't depend on D. It doesn't also depend on this thing, like the difference between P max and the P second max. And like previous analyses of this kind of thing, they did have like dependencies on these two quantities. So we really get an absolute constant over epsilon squared. OK, cool. So that's something about P max and like a nice open problem for you to think about, how to prove that in elementary fashion. Here's another example that we looked at in our first paper, testing uniformity. So I'll be a bit vaguer about this one. So testing uniformity is you want to know if all the p's are basically about 1 over d. So here's some like vague intuition. So all the p's are about 1 over d if and only if p max is as small as it can possibly be. Which, and we just saw p max is sort of basically proportional to lambda 1. So it's kind of like if and only if lambda 1, the length of the first row, is sort of as small as it could possibly be. Which is sort of saying the Young diagram is not really like triangular. It's sort of as rectangular as it could possibly be. Which is kind of like saying if it's rectangular that the lengths of the rows are kind of all about the same. Or you might say the variance of the row lengths is about as small as it could be. And the lambdas always sum up to n, the total number of boxes. So saying the variance is small is also the same as saying that the sum of the squares of the lambdas is small. So all of this long story is just to say that if you believe this intuition, then like, you know, you might think that the unknown distribution is close to being the uniform distribution, sort of if and only if the sum of the squares of the row lengths is sort of small. And it turns out that that actually is a good intuition. It's kind of correct. But how can you analyze this? I mean, this is ultimately kind of what we got at. But in order to analyze this, it seems at the very least you should be able to do something like figure out what is the expected value of the sum of the squares of the lambdas as a function of the p's. But that looks a little weird. It looks like you're not going to be able to do this with combinatorics, right? Like understanding the length of the longest increasing subsequence as a function of the p's seems kind of plausible, but like how could you understand anything like the square of the longest increasing subsequence length plus then the lambda 2 has something to do with the longest 2 increasing subsequences, and you square that? Like, it doesn't look very promising. And indeed, we don't exactly, let's say we don't exactly know how to understand this quantity, but we can understand a very similar looking quantity perfectly, which is kind of amazing. The quantity we can understand perfectly is the expected value of this expression. It looks kind of odd. You don't have to care about it that much, but it's like the sum, almost the sum of the lambda i's, but like you subtract I from lambda I, There's also some other correction term here. So it's some weird expression in the lambdas, but it looks pretty similar to this, which is good because this is what we cared about. And as it turns out, we can exactly compute this like 100%. And there's just a simple formula for this in terms of the PIs. Why? It has something to do with the representation theory, which I didn't tell you anything about. And it goes back to the connection of all this stuff with representation theory of the symmetric group. And it turns out this expression, which I called sigma 2, is exactly the value up to a constant of the character of the symmetric group indexed by Young diagram lambda evaluated on the transposition 1, 2, or any transposition actually. And there's some theory for why that is, and because of that theory, we can actually just literally write down a simple formula for this thing. So I won't go more into that, but that's some stuff that we used in the paper as well. So to sort of summarize all the methodology we used for these problems, it was half the time it was some probabilistic combinatorics involving increasing subsequences, and half the time it was some representation theory of symmetric group, and this theory of something called shifted symmetric polynomials like this sigma 2. Okay, so this slide says conclusion, but actually it's a very long conclusion, well maybe 5 minutes or something, so it's not like I'm going to be done in 30 seconds. So what are the conclusions? I mean, I didn't tell you too many details about what we did. But I really enjoyed working on this problem because it connected to a lot of interesting different areas, like the representation theory and the longest increasing subsequences and the algorithms and the quantum. One recommendation I have is if you want a nice bedtime reading book, like this book by Dan Romick called The Surprising Math of Longest Increasing Subsequences. It's a beautiful book. It's extremely enjoyable to read. It tells you about all this beautiful math connected to longest increasing subsequences. It's good to check out. And let me just tell you a little bit about the story of, a little bit more of the story of longest increasing subsequences. And I can fit it into our framework. So just imagine you're doing this whole story with the longest increasing subsequences where the p's are the uniform distribution. Okay, so you have random words with the uniform distribution on letters 1 through d. And in fact, imagine that d is much, 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 much bigger than n. Okay? In fact, if you want, you can call it d equals infinity. But what is the point of imagining this? The point is that if d is much, 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 much bigger than n, then when you draw n random symbols between 1 and d, you'll never get any repeats. Okay? So they'll just be distinct. And also, when you care about longest increasing subsequences, it doesn't matter the actual magnitudes of the numbers, right? It just matters their relative comparison. So if you have a random string of these distinct letters, it's exactly like having a random permutation in terms of increasing and decreasing subsequences. So all of this is just to say that this is imagining you have a random permutation. You randomly permute the numbers 1 through n, and you look at the longest increasing and decreasing or whatever subsequences in this permutation. And this problem of understanding increasing subsequences and random permutations has a very, very long and rich history in combinatorics. And lots of beautiful stuff about it is known. And it's sort of a special case of what we had been studying. For example, the distribution you get when you run the RSK algorithm on a random permutation is a distribution on Young diagrams that's called the Plancherel distribution because of some reason to do with representation theory. And the mathematicians love to study it. And there's many, many beautiful theorems about the shape of lambda now when n gets large. Random permutations on a large n. For example, suppose you do this. Here's an example of what it looks like when n is 1,000, and it's a random permutation 1 through 1,000. You do the RSK. It looks like this. And so this width is the length of the longest increasing subsequence. And now with permutations, everything is symmetric. So this is the length of the longest decreasing subsequence, and they're basically the same asymptotically. You can ask how large this is, and that was a famous open problem in combinatorics. What is the sort of asymptotically, what is the longest increasing subsequence in a random permutation of length n? And it was famously resolved. It's asymptotic to 2 times root n. And they weren't satisfied with that. They wanted to go even further. So it's now even known that the second order term is order n to the 1/6. And that's also considered very interesting because it's not the square root of the main term as you might expect. It's the third root of the main term, which is something to do with this KPZ phenomenon, which I don't know about. And they still weren't satisfied with that. They're let's determine the leading constant. And it's it's like a random variable, zeta 1, which is distributed according to this Tracy-Whittem distribution, which has something to do with random matrices. So there's like all sorts of beautiful things going on in this story. You can also, like another move they love is to like rotate it like this. And then you can like think of this as like a curve. And they know that as n goes to infinity, like asymptotically, it tends to this exact curve with the arc sign and so forth. And there's like some beautiful reasons for that. So yeah, so they know all sorts of amazing stuff about this. And all this amazing stuff they know is just about random permutations, which is kind of like a very special case of the thing that we studied, right? So this is all for like the uniform distribution where you think of d as like infinity. And the case of finite d is actually somewhat less studied. They tried to study it somewhat, but not as much. And the case where not all the pi's are the same is also less studied. And the case where you don't like, the first move they always do is just assume n is like going to infinity. But the case where you don't just let n be really large, but actually care about how n interacts as a function of d is even less studied. But like all these things are exactly what you need to understand like quantum tomography and quantum PCA and everything. So all these like great combinatorics questions, generalizations of them are totally motivated by quantum mechanics. And I think there are many more beautiful theorems in this area waiting to be discovered. OK, thank you. Sure, yeah.
Is a very elementary question. You said that some of your bounds indeed do not depend on the dimension.
One of them, yeah.
One of them.
Yeah.
But in the derivation of somewhere, the dimension does play a role. So, I mean, would I be able to say something about the? I'm more a physicist, so if I have a completely unknown quantum system, I don't know if it's a qubit, a qubit, or even infinite dimension.
Yeah.
I want to find the maximal eigenvalue.
Yeah.
Would I be able to do that without this information about that actually this is a d equal 10 state? Would I just
I guess you kind of need to sort of know d or an upper bound on d. For example, one thing I didn't exactly talk about is what exact measurement you do and like the complexity of implementing that measurement. So for the measurements where you just want to learn things about the p's, it's a pretty explicit measurement that can be done in principle with like a quantum circuit with complexity that's like polynomial in n in log 1 over d. But I guess I never really thought about this before. I sort of always assumed that like d is sort of known. Yeah, that's all I can tell you, I guess.
So, like the earlier techniques for tomography,
Yeah.
they didn't go via this lambdas at all?
No, actually they did. Actually, I didn't get really a chance to mention this, but so tomography, I can't really. The early techniques for full tomography, they were quite different. But if you only want to learn the p's, then actually we didn't do anything new. We just analyzed known algorithms differently. So like the known algorithm for learning the p's is sometimes called a Kyle-Werner algorithm, although it's discovered earlier by some other people as well. But that algorithm is to just take the lambda that you get and just output that you think the largest p is lambda 1 over n, and the second largest p is lambda 2 over n, and the third largest one is like lambda 3 over n, just like in the classical case, actually. That's the Kyle-Werner algorithm. And yeah, we somehow, John and I just like analyze it better than it had been analyzed previously. So for example, previous analyses had shown that that'll give you an epsilon accurate estimation of all the p's, provided n is like d squared log d. And we got rid of the log d. And then we also showed that you can also get the v's in the same number of samples, d squared. Yeah, but that algorithm with the, I should have mentioned this, that algorithm with the Schur-Weil duality and the Young diagrams was previously known.
So how do you get the vectors?
How to get the vectors? Yeah, it's more complicated. First you learn the v's, or the p's. And you project into that subspace. And then you do something with like representation theory. Here actually it's like even more complicated because you can't do a projective measurement. You need to do this like POVM with like infinitely many outcomes. But basically it's something like in the representation theory of like the unitary group, there's something called the highest weight vector. And it's sort of well defined. And you do a POVM that kind of like rotates the space, but like it gives you an outcome with its outcome is a vector, and like the sort of the probability of getting that outcome is like proportional to that vector squared dot product with this highest weight vector. So yeah, the long story short is like some representation theory. Yeah, I don't know if I can explain it better than that. And that algorithm was also suggested previously by Kyle, and he did some kind of analysis of it, but like kind of with a different angle on it than we used. But we also didn't invent that algorithm, like we just analyzed it differently.
So previously the d cube was coming because they were taking d squared to get the p's and then another d to get the p's, is it?
No, previously the d cubed, well, the d cubed like appears in a paper that isn't even about quantum. Like just somebody noticed that like, it was a paper about like compressed sensing, but somebody noticed that like it actually solves this tomography problem with d cubed samples. For the long time, the only thing known was like d to the fourth, and it's like some super elementary thing that's in like the Nielsen-Chuang book where you just do like very simple measurements separately on each of the particles. You measure them in all like the Pauli basis. And that gives you a d to the fourth algorithm. Yeah.
So if you are required to do separate measurements, not global measurements,
Yeah.
is it optimal or is not normal?
Yeah, I don't know a lot about that. Maybe John, you know some stuff about that?
D cubed is optimal there.
Then d cube is optimal.
Did you prove that?
No, that was in that other paper with Aaron Harrow and all.
Oh,
Okay.
okay.
I see.
Or at least they mentioned it in QIP, and I think it's forthcoming
I
in
see.
an updated draft.
Okay.
Yeah, that's a good point because these algorithms use like highly entangled measurements. So like in practice, it's probably, well, maybe it's debatable, but like it's pretty challenging maybe in practice. And like in practice, people only like to use like the local measurements. And it seems like to get this optimal result, you have to use entangled measurements.
Do you know some things about higher moments in the W?
Yeah, so roughly speaking, the way we get like more, it actually goes into like more of our lower bounds, but like you can kind of get, you can relate like higher moments of the lambdas to some like more complicated character values, and you can get some like explicit but somewhat painful formula for them using the representation theory, and like that's what we end up leveraging, these somewhat painful formulas for the higher moments.
Other questions? Okay, so then really thanks for this.
Thanks, Nicholas.